Under multiplication, please. And the little subheading for the multiplication thing is multiplying by, if I can find it here, multiples of 10. Anybody know what the multiples of 10 are? Caleb, they are
10,
10, 20, 30, 40, 50, and so on and so on. We don't have to write them all down there. You can also use what we're going to talk about today to do the multiples of 100, which if you're thinking about are 100, 200, 300, and so on and so on and so on. If you can do single digit multiplication, doing multiplication by these multiples of 10 and 100 is very much similar, and you can do this. And here is the deal. And the book strongly suggests this, and I think it's a good idea. Okay? When you multiply by these multiples of 10 and 100, comma, let the zeros, the book says to let those zeros hang out. Or hang over, what do they say? Probably hang out. Hang over has a bad connotation to it. Hang out. And I'll explain exactly what that means in just a second. Let you write that down, because I know you're diligently writing down everything. Every word I say, just here is your example. Let's say you have 536 times 30. We haven't yet gotten to the double-digit multiplication yet, but you don't need to just yet either, because 30 is a multiple of 10. So when you write this problem down, what they mean by let the zeros hang out, they mean to do this. Put the big number on top, 536 times, did you do this last year?
Yeah.
Okay, if it ends with a 0, leave that 0 outside, out past that. Because to do this problem, it's the same as multiplying 536 times 3, except you put a 0, however many zeros hang out, those are the ones you just start with before you start multiplying. So that 0 starts there, and then you just multiply 3 times 6 is 18, 3 times 3 is 9, plus 1 is 10, and 3 times 5 is 15, plus 1 is 16. We always like to put little bubbles or clouds around our answers. Okay, and it wouldn't matter. You could do it with, another example would be, let's do 536. If you had 536 times 300, same thing is true. You take 536 times, put the non-zero digit underneath that ending number and hang out those 2 zeros there, and they just come straight down. This time you start with 2 zeros and multiply by the 3. 3 times 6 is 18, 10, 16. And it would be the same thing if you had 536 times 3 million. As long as they end with zeros, you can use this one. Did I do something wrong? As long as they end with zeros, you can do that same thing. So I could write this as 536 times 3 and let all 6 of those zeros hang out over there. And just start with all 6 of those zeros dropping down. And then multiplying by that whole 18, 10, 16 thing. They won't ask you to do numbers with that many zeros in them, but it's the same thing that you could use no matter what. Doesn't work if this would have another number besides 3 there, 3, 4, or whatever, but as long as it's a single digit with zeros following it, you can do that. Matthew?
What would happen for like example if it's 300 times 300?
That's a good question. Works the same way. let's do 400 times 400 just to use some different digits. You can do the same thing there. It doesn't matter which one goes on top because they're the same. You're going to have 400 times 400. You're going to still drop those two ending zeros down. And then you're going to multiply 4 times 0, 4 times 0, 4 times 4. And you'll get 160,000, which is what the answer should be there. Let's look at another one. Now, please make sure you notice this. 60 times 45. Because of the, if you remember, the commutative property of multiplication, just because the 60 comes first doesn't mean it has to be on top of my, when I do my multiplication problem. You can always flip-flop multiplication things around, just like 6 times 8 is 48, just like 8 times 6 is 48. Those can be mixed around. So when you write this problem out, what are you going to do? You're going to put the 45 on top, and you're going to write the 60 below it like that. You're letting this one hang out, baby. Hang out. You bring that straight down right away, and then just multiply by the 6. 6 times 5 is 30. 6 times 4 is 24, plus 3 is 27. There it is, your answer. Sometimes I like to do my bubbles like this. You actually pick your pencil up, makes them nice. It does look like a whole bunch of hills. Let's do one that is money. What about $1.43 times 200? $1.43 times 200. By the way, it's always good, 5th graders in math, that when you look at a problem like that, in your mind, you should have some sort of a decent guess as to what the answer should be. I mean, so like, is the answer going to be like 2 million? I mean, if you took $1.43 and multiplied it by 100, let's say at least a reasonable guess that your answer should be. Luke? Yeah, at least 200. You know it's going to be bigger than 200 because if it was $1 times 200, it'd be $200. If it was $2 times 200, it'd be $400. So you know it's going to fall between there. That way, if you get like 17 million as an answer, you'd probably want to look at it and go, boy, that doesn't seem like what I should have gotten there. So here's what it looks like, $1.43, and you're multiplying it by 2 and letting those zeros hang out over there. Now I'm going to get this, and I'm going to get 6, and I'm going to get 8, and I'm going to get 2. And here's one of those cases there. So is my answer going to be $286? Does that sound like it would be reasonable? Because you put the 2 cents over there? Yeah. As we said, it should be at least $200, and probably more because you've got 43 cents there. So make sure if you're multiplying something with money, you give your answer in terms of money. Let me give you one to try before I set you free here. How about this one? You do this one. 55, well, let's do it this way. 300 times 55. Do that multiplication problem for me.